Hello dear children, and good to see all of you in the science class once again. We are discussing chapter number 13, magnetic effect of electric current. We have discussed the nature of magnetic field around a bar magnet and also nature of magnetic field around a straight conductor carrying current. We are going to move ahead with the topic and learn the new thing in today's session. This is what we have already learned in the previous video lesson, dear children, magnetic field around a current carrying straight conductor. And you all have studied that the magnetic field is in the form of concentric circles, and the closeness of the concentric circular lines depends upon the amount of current passing through the conductor. As we increase the amount of current passing through the conductor, the circular concentric lines will be more close to each other near the conductor, and as you move away from the conductor, the lines will be far apart from each other. Now in today's session, we will be learning the new thing. Consider that instead of a straight conductor, we have a conducting wire which is in the form of a loop. Yes, look at the screen. This is not a straight wire. The wire has a loop. It is circular in shape. And towards the bottom of the circular loop, let's connect a battery. And we will complete our circuit by connecting a plug key. And this is how we have made a circuit with a loop at the top of the battery and the plug key connections. Alright, so this is what is the loop. Now we have to find out how will be the magnetic field look like around a closed conductor or around a closed circular loop. Alright, so can you just guess? I have also shown the direction of flow of electric current here, and as you pass the electric current, what will be the nature of magnetic field? Can you all guess it? Let's perform a small activity to check out how does the magnetic field look like when the conductor is in the form of circular loop. So for that, what will we take is a plastic board, and to the plastic board we have made two holes. Now from this two holes we will insert the copper wire for, we'll take the turns of the copper wire for say 50 turns or more than 50 turns, and we'll insert copper wire from one hole, take it out from the other, then again keep doing it for almost 50 or more than 50 turns. So it will look like this, and the two ends are kept free so that we can pass current to the from the two free ends. You understood how the assembly is done? A plastic, you can say a frame or a plastic board, two holes to the plastic holes, and then a copper wire of almost 50 turns is been taken and a circular loop is formed. Then what we will do, we'll sprinkle iron filings on it, like how we did for the straight conductor. Alright, and I'll connect the battery here because we have to pass the electric current through it, because the moment we pass electric current through this assembly, the iron filings will arrange themselves in a specific manner, and that will be the nature of the magnetic field around a closed loop. On the closed circular loop, we have taken two places wherein we made the two holes. Alright, so after passing current, you will see the nature of the magnetic field in this manner. Can you observe that at these 2 points where we made the holes, there we can see concentric circles, and as we move towards the center of the circular loop, the magnetic field lines, they appear to be straight. Alright, so let's understand this in a better manner. I'll try to make it more clear to all of you. So children, suppose say I have this circular loop or circular conductor or circular conducting wire like this, And let's assume that the electric current is passing through this circular conductor in this manner. Now I can just make small pieces of this circular conductor, and every small piece will act like a straight conductor to me. You understood what I said? If I cut this circular wire or circular conductor into small pieces, every piece will act like a straight conductor. Now what we will do, we will select 2 points on the circular loop in this manner. This is first point and this is second point. And let's observe the magnetic field which is produced over here. And then we'll also have to find out what will be the direction of magnetic field. Okay, so at these 2 particular points, we will understand how does the magnetic field look like and what will be its direction. As I told you that every small point, every small piece of the circular loop acts as a straight conductor. So the direction of magnetic field can be found with the help of right hand thumb rule. So at the first point, what will I do? I will hold the conductor in this manner. Can you see that the thumb is pointing inside your screen and the curved fingers are in this manner? And right hand thumb rule states that when you hold the thumb in the direction of the flow of the electric current, the curved finger gives us the direction of magnetic field. So here we have, we can clearly see that the magnetic field is in the direction of the curved fingers. So how does the magnetic field look like? It will look like this. Can you see the arrows? The magnetic field is coming in the outward direction. The arrows are coming in the outward direction, that is along the curved fingers. Now let's see what will be the direction of the magnetic field at the other point. So I have to hold my thumb in the direction of flow of electric current. So we will hold it like this. Look at the direction of the thumb. It is in the direction of the flow of electric current. And the curved fingers will give you the direction of the magnetic field. So how will it look like? It will be like this. Can you see the arrows? The magnetic field is coming in the outward direction. From inside to out it's coming. Alright. Like this, if I hold the circular loop at any place other than these 2 points, every time I will observe that the magnetic field lines are coming from inside the circular loop and then it is coming out, and that is the direction of the magnetic field. Look over here. We have holded the circular loop at 2 more places, and you can see that the magnetic field lines are coming from inside the circular loop and it is coming out. Now this way, suppose if I combine all these magnetic fields and then I'll check out exactly how it will look like. So your answer is this. The magnetic field will look like this around a closed loop or a circular loop. I will sum up it in this manner, that at every point on the circular loop, the magnetic field is in the form of the concentric circles. At the center, if you see, the magnetic field line appear to be straight. So as you move away from the point towards the center, it becomes straight. Now can you just imagine and can you recollect the magnetic field of a bar magnet? Does this magnetic field resembles like a bar magnet? Your answer should be yes. Can you see there on the screen? I have taken a bar magnet, and can you see the similarity between the magnetic field of the circular loop and the bar magnet? Both the fields or the nature of the magnetic field looks the same. So we can say that the nature of the magnetic field in a circular loop is also similar to that of the bar magnet. So if I reduce the size of the circular loop, it acts as a bar magnet. Alright children. So look at this. The magnetic field lines are concentric circles at every point of a current carrying circular loop. The direction of the magnetic field of every section of the circular loop can be found by using right hand thumb rule. This is for the theoretical part or the theoretical explanation of the diagram. Alright, now suppose if you are asked to draw a labeled diagram of the magnetic field around a circular loop, this is what is the diagram which you have to draw. So here, this is what is your circular loop. We have selected 2 points, and around the 2 points, we have drawn the nature of the magnetic field. You can see that at these 2 points, the magnetic field is in the form of a concentric circle, and as you move away from the circle and come at the center of the circle, it looks as if it is a straight line. So we can sum up it like this. At the center of the circular loop, the magnetic field lines are straight. Each segment of the circular loop carrying current produces magnetic field lines in the same direction within the loop, and the direction of the magnetic field at the center of the circular coil is perpendicular to the place of the coil, that is along the axis of the coil. This is important point. So these 3 points for your theoretical explanation. Alright children, so let's now move ahead to the next topic. What is a solenoid? So a coil with many circular closed turns of insulated copper wire, which looks like a cylinder, is a solenoid. You can see it on the screen. You can see that a copper wire is coiled in the form of a cylinder, and that assembly is called as solenoid. So it's easy to make solenoid at home. You can take a pencil or any you can take a paper roll, and around a paper roll you can start winding the copper wire, then take out the paper roll or a pencil, and what you get is a solenoid. So this is what is solenoid. Now the question is, how does the magnetic field look like in a solenoid? How does it look like? Does it look like a magnetic field around a bar magnet, or a circular loop, or a straight conductor? Let's understand that. Now from the picture of the solenoid, you can make out that there are so many circular loops there, and they all are joined together. So what will I do? I'll take the circular loops like this. I'll break the solenoid and I'll take each and every circular loop in this manner. Then to find out the nature of magnetic field, I'll connect the battery here. Alright, and I'll imagine that all the circular loops are connected to each other. Now in the previous discussion we have studied that when the conductor is in the form of a circular loop, at every point on the circular loop we get a magnetic field in the form of concentric circle. So at this point, everywhere you will see that the magnetic field is in the form of concentric circle like this, isn't it? Now children, suppose now I joined all these circles together. If I connect them and make it in the form of a solenoid, then all these circular loops will give me a combined effect. It will become one component. And how will it look like? Look at this. It will look like this. When I join all the circles in the form of a solenoid, it will look like this. And more precisely, if I want to show you, the nature of the magnetic field is in this manner. We have combined all the magnetic fields of every individual circle and joined it, because in a solenoid every circular loop is joined to each other, and the magnetic field looks in this manner. Is anything clicking in your mind? Is it similar to any of the things which you have learned? I think you have got the answer, but I'll explain you that in the next slide. Now children, in the solenoid, one pole acts as a north pole and the other end acts as a south pole. Now the question is, now we don't know which is north pole, which is south pole. So how do we know that which end is north pole and which end is south pole? That we can find out only if we connect a battery to the two free ends of a solenoid. So let's first do that. We will connect a battery here. So we have connected a battery. Now you all are aware that the current flows from the positive terminal to the negative terminal of the battery. That's the conventional flow of electric current. So it's going like this. Look at this, it's going up, then through the coil it's coming down, again going up, and this way the current will circulate, and this is how it's coming out and the circuit is getting completed. Now how will we come to know that which is the north pole and which is the south pole? So let's come to the direction of the flow of electric current. Now literally you have to imagine that you are holding one ring in your hand and you are standing in that direction towards the direction of the flow of electric current. And when you hold this ring in your hand, you have to imagine it in this direction. You will understand that the current is flowing clockwise. So have a look at this. This is how the current is flowing, isn't it? So I have put the arrows there, and at the center, suppose if I join these two arrows, it's giving me this shape. This is S shape. S stand for south. So when in the circular loop, if the current is flowing in clockwise direction, that is the south pole of the solenoid. You got this, children? So the coil of the solenoid where the current is in clockwise direction, that is its south pole. Now come to the other part of the solenoid. Look over here. Alright. Here if you see, literally again, you have to literally go there and try holding the ring in your hand and check the direction of the current. And here you will observe that the current is flowing anti-clockwise. And look at this. This is how I have shown the arrows. And if I join the arrows in this way, it's giving me the north pole. So the side of the solenoid, the coil of the solenoid where the current, if you observe that it's anti-clockwise, that is its north pole. So the north pole current flows in anti-clockwise direction. So in the exam, they'll just give you the solenoid and will give you the question, identify the north and south pole. You can draw the battery in whichever polarity you want. Either you take, positive towards your left or negative towards your, left. And like how the flow of electric current you show in the solenoid, accordingly you decide the north and the south pole. So this is very important. At south pole, the current flows clockwise, and at north pole, the current flows anti-clockwise. And this is called as clock face rule. Alright, so this is a new term for you. So I have shown you this in the next slide. Look at this. Look at the polarity of the battery here. Alright, and accordingly the current is flowing through the conductor. So depending upon the polarity, you can guess which is south pole, which is north pole. Keep this in mind, very fixed, that at south pole the current flows clockwise, and at the north pole the current flows anti-clockwise. And how will you decide the flow of electric current? You will decide that by taking the battery, in which direction you are connecting the battery to the solenoid. In the other figure, look at this. The polarity of the battery is shown in the other manner. Alright. Accordingly, you will mark the direction of flow of electric current. And if it is clockwise current, it is south pole. And if it is anti-clockwise, it is north pole. So in both the figures, you have two solenoids, and I have described how you will identify the north and the south pole. I hope you understood this, children. This is very important part of the lesson. So I'll sum up like this. Solenoid behaves like a bar magnet. You must have identified. I ask you, can you just recollect how does this magnetic field looks like? Yes, it's like bar magnet. When an electric current is passed through it, it produces a magnetic field, and that magnetic field resembles the magnetic field of the bar magnet, wherein the magnetic field lines, they emerge from north pole and merge at the south pole. Very, very important thing you will keep in mind, that the magnetic field lines are in the form of closed loop. This is very, very important point which you have to keep in mind. It is in the form of closed loop. It it emerge from North Pole and merge at the South Pole, and inside the bar magnet it flows from South to North Pole. Now look at the similarity between the magnetic field of the solenoid and a bar magnet. It exactly looks similar. So like in the bar magnet, the field lines emerge from one end and merge into another. In solenoid, the same thing we observe. The field lines behave in the same manner in case of solenoid. Alright, this is important point. Then one end of solenoid behaves as magnetic north pole and the other end as magnetic south pole. And we discussed how will you find out which is north pole and which is south pole, and it is completely dependent upon how you connect the battery to the two free ends of the solenoid. Alright children, so another important, very important points here. The magnetic field lines are parallel straight lines inside the solenoid. Look at this figure. Inside the solenoid, the magnetic field lines are parallel to each other. It means magnetic field is same at all points inside the solenoid. Very important point. What is the nature of the magnetic field inside the solenoid? The magnetic field is same at all points inside the solenoid. That is, in the other way we can say that magnetic field is uniform inside the solenoid. Alright, and the magnetic field produced by the solenoid is very strong as compared to the straight conductor, circular loop or anything else. So magnetic field produced is very strong in case of a solenoid. And the strength of the magnetic field, it depends upon certain factors, that is number of turns in the solenoid. How many times you are turning the copper wire and you know making it. Number of turns is very important factor. As number of turns increases, amount of electric current passing through that increases. If the current is more, magnetic field will be more stronger. The strength of current in the solenoid, as you increase the current, the magnetic field will be very strong. And the nature of core material used inside the solenoid. This is another very important thing children. Suppose if I take a soft iron core and keep it inside the solenoid where you see those parallel lines, you will observe that this soft iron core, it becomes a magnet because magnetic field is produced when we pass electric current through it, and that is called as an electromagnet. Okay, so the iron core which is placed inside the solenoid, it becomes an electromagnet after passing an electric current through the two free ends of the solenoid. Is this clear to all of you? Now along with this, I have an assignment for you. I want to repeat once again that the part which we have taken in today's video lesson is the most important part of the lesson. And on this part, you will 100% get questions in the examination. So please prepare it thoroughly. So look at these questions. What is meant by solenoid and how does a current carrying solenoid behave? So it behaves like a bar magnet. And give its main use. In the use, what will you write? It is used to make an electromagnet. And I told you what is the meaning of electromagnet. Question number 2. For the current carrying solenoid which is shown in the figure, draw magnetic field lines and giving reasons explain out of the 3 points A, B, C at which point the field is maximum and at which point the field is minimum. So actually to give you the hint, I have given you the nature of the magnetic field there. And how will you draw the magnetic field there? Because you have to see the arrows. According to the arrows, you can make out which terminal is positive, which is negative. Based on that, you can find out which is north pole, which is south pole. Once you get the north pole, then the magnetic field lines, they emerge from the north pole. Accordingly, you can give the arrows. So I have given the hint and accordingly you check out and just see that. Then what are magnetic field lines? Justify the following statements. Magnetic field lines are closed curves. I told you to remember this. How will you justify that? it emerged from one end and merged at the other end, and inside the solenoid or a magnet, it goes from south to north end. This is how you will, find out the answer. Clear? So I hope you will complete the assignment and keep the stuff ready. See you all in the next video lesson with a new topic. Till then, bye and take care all of you.